Okay, hello everyone. Welcome to the fifth session. No, it says 4, but I'll update that later. Today we're just going to sort of introduce the idea of parallel computing and not do too many examples. On Thursday, we'll go into one specific way you can actually implement parallel computing for yourself. So to sort of start this off, has everyone heard of Moore's law before, or anyone heard of Moore's law? Anyone tell me what Moore's law is if you've heard of it? Okay, no. Okay, so Moore's law is not really a law. It's kind of misnamed. It's more of an observational trend that you can see in the data. So Gordon Moore, I think is his name, was one of the founders of Intel. And he basically noticed that on a given like microprocessor chip, the number of transistors on there doubled roughly every 2 years. Basically, the transistor is like your building block of your processors. So the more transistors you have, the more sort of calculations you can do on your processor. And we can see this in this sort of microprocessor trends graph. So the number of transistors is shown in orange. It's this line on the top. And if you notice, this is a logarithmic scale on the y-axis. So any sort of straight lines here means it's exponential. So exponential growth. And you can see that Moore's law predicted back in like the sort of 60s, 70s time, and it still holds to today. The only thing is, a lot of the associated benefits of Moore's law, like faster compute power, has started to sort of taper off a little bit. So this is what we can see on the other lines. So if we look at what's called the single-threaded performance, so how fast a single core inside your processor is, that was also increasing exponentially for a number of decades, and it slowly started to taper off around sort of mid-2000s. And the main, so you can see it's sort of starting to taper off at the moment. The main reason for this is the frequency at which you can clock your chips is sort of leveled off around the same time as well. So the frequency or the clock speed is the sort of length of time it takes for one cycle of your CPU. So like one instruction, for example, an addition would take one clock cycle. So if you shrink the time between cycles by a half, you can effectively double the number of calculations you're doing. This has tapered off completely. And the main reason for this is as you've shrunk microprocessors down and down and fit more transistors onto the same sort of die area, the same size, and you increase the frequency, you also increase the power draw. So you need more and more power to run it faster and faster. And most of you are physicists, you know, if you put power in, it has to get dissipated somehow. You have to get rid of the heat. And if you don't, the components can get very badly damaged. And also you can start to introduce errors as well if it gets too hot. So effectively, we're sort of at physical limits of like how fast a given processor can be given the sort of materials and the design processes that we're using. So what you...
I have a stupid question. So the single thread performance is almost, not changing anymore. But what is the point of increasing transistors?
Thank you for that question. So yeah, the question was, what's the point of increasing transistors if the single-threaded performance isn't improving that much anymore? And yeah, so we're still increasing the number of transistors, but what's happening is those transistors are just going to create more logical cores on the same die. So instead of just having one core, which was the norm for the past sort of 3 decades before the 2000s, most processors were just one processor per like CPU die. And most of your algorithms were sort of single-threaded performance, and a few niche cases for like supercomputers by networking a lot of these processors together. Whereas they started to realize the only way you can actually increase the performance now is by putting multiple CPU cores, multiple cores on a CPU die. So we looked at it before in some of the previous sessions, an actual sort of diagram of the CPU, and they're physically like copy pastes of one another on the CPU die itself. So while they're not faster, you can do more things, because if you can do things in parallel, then effectively you can sort of double the amount of compute if you double the number of cores. And today we'll be talking about exactly what you can and can't benefit from.
Multi-thread performance is actually increasing.
Yes.
Okay.
Yeah, exactly. This is only CPU data as well. So this is just your sort of general purpose CPUs, but sort of, I guess around the 90s from there, you start getting other coprocessors, so the GPUs that specialize on graphics, which have, so this is what order of magnitude, like 10 to 100 for the CPUs, but the current GPUs are sort of between 10 and 20,000 cores instead. So there's a few orders of magnitude more. We'll talk about that more in the final week. So yeah, so this graph is really important. It basically tells us why we actually need to focus on parallel computing, because in the old days, if you had a problem that was too big to solve with the current processors, you didn't have to speed up your algorithm, you just had to wait a year, and then the processors would be fast enough to deal with it. Whereas now, you don't have that luxury. You have to focus on parallel computing because it's the only way you can actually get more performance out of your current hardware. So yeah, as a summarization, processors aren't really getting faster. They are a little bit, and they're getting a bit smarter in ways, but the performance is not exponential like it was before. But the sort of investment from the industry is getting multiple cores as well. So going towards giving you more processors to work with instead of faster processors. The trouble with this is you actually need to do some work, right? You can't just get your single-threaded code and have more processors and it just runs faster. You have to actually work to be able to do that work on the multiple cores. So this is going to be, I guess, a quiz for you guys as to what sort of tasks can benefit from parallelization. So first one, which hopefully you're all familiar with, is matrix multiplication. So on this spectrum, on the left-hand side, you get no benefit if you have multiple cores for doing things. And on the right-hand side, you get a huge benefit if you put in more resources, so more processing cores. So where do you think matrix multiplication lies on this? Exactly. Right. So each element of your result matrix could be calculated on a different core. And they're all independent operations, so they can effectively happen at the same time. So another thing we like to do in physics a lot is Monte Carlo simulations. For people who aren't too familiar, Monte Carlo simulations are basically just running sort of independent trajectories with sort of random numbers. And what you want to get out of it is like some average statistics afterwards. So like, for example, if you're sort of playing a game where someone stands still and they want to flip a coin, if it's heads, they move to the left. If it's tails, they move to the right. And you want to ask what's the sort of average position they end up at after like 10 of these flips. You would do something like a Monte Carlo simulation for this. This is used everywhere as well. It's a massive technique. So any idea where that would be on this graph? Yeah, okay, massive speed up. Because all of your trajectories are independent of one another, you can have each CPU core run the trajectory independently of the others. So if you have 1,000 trajectories you need to run and 1,000 CPU cores, you can effectively reduce the runtime to just a single episode, a single trajectory. So next one is like numerically solving a differential equation. So this is like sort of Newton's law. So you can think of like the n-body problem that was in one of the optimization problems. Where do you think this goes on the spectrum? No idea? Yeah, exactly. But it's more on the left. I wouldn't say no speed up because it depends on your problem, right? So if you have n-body calculations, like you can calculate like the force between the Earth and the Sun at the same time as calculating the force between the Earth and Mars, for example. So there's some speed up, but there's still some inherent sequential steps that you need to take to work things out. Because to work out the force that you need to update to the next state, you need the current state. And so there's some ordering that you need to still respect in that case. more fun example. So if you're like making a game, like where is that going to go in this sort of spectrum?
So
It's Skyrim, if you're wondering.
also almost the same position as a differential equation.
Yeah.
Some speed as still,
Yeah.
because of graphics.
Yeah.
Which is always matrix multiplication.
Yeah, exactly. So it really depends. Game simulation is so complicated, it's really hard to break up. But I would say it's more towards the left-hand side of this graph.
What's the difference between differential equation and the game simulation? For physics, right?
Exactly, right? It's very similar. The main thing about playing a game is like, especially if it's like a first-person game, is every time you're rendering a frame on the screen, you can use like a graphics card, right? To find out what's the color of each of the pixels in parallel. That bit can be completely sped up, but you can't work out what the next frame is going to be until the user does something. And you can never really predict what the user is going to do until they actually do it. So there's some element of sequential programming, and there's some limit to which if you had infinite resources, you still can't make it faster because there's some things you just need to do one after the other. Okay, well done, everyone. Everything's correct. So you could sort of intuitively guess which ones would benefit from a speed up, but one way we can sort of formalize this process is by using a sort of dependency graph to see which tasks depend on one another. So if we have, how many is this? 7 tasks altogether, so A to G. In brackets, it's just like a unit of time that each thing takes. So A takes 2 seconds, but C takes like 10 seconds, for example. Doesn't have to be seconds, they're just arbitrary units of time. So a normal algorithm, let's say, would just sort of process these one after the other. They'd do A, then they'd move on to B, then move on to C, until they finish with G. And G is like your final result that you want. And it would take 28 units of time to actually process this. But in order to actually know how much this can benefit from parallelism, you need to know which tasks depend on the previous tasks to finish. So if we get some information like B and C depend on A, when D and E depend on B, so on and so forth, we can sort of draw a graph that represents these dependencies. So the dependencies sort of listed out in the bullet points are just represented by these lines. So a line going from A to B means that B depends on A in that case. And this is a nice visual representation for us to see which tasks can be done at the same time. So for example, as soon as you finished A, B and C are independent of one another. So you could process them at the same time. And there's something on this graph as well, which points out the sort of minimum time it would take to actually finish processing these results. So basically the longest path from A to G is called your critical path. And this is about 18 time steps. So even if you had infinite resources, the sort of minimum amount of time you could take to process this particular task is 18 units. So your only speed up is like 1.5 times in this case. So I guess the question would be sort of how many processors would you use to process this graph and not waste resources? So I've got a guess of 3. Any other guesses?
Sorry, 2.
Okay, guesses of 3 and 2. So why did you say 3?
The first branch takes 2. The second branch takes 1, and 2 as
Yeah,
as 3.
I think I know what you're saying. 3 is like the intuitive answer, right? Because you can see that as you finish B, B will be finished much faster than C, and then you have 2 more tasks, D and E. And so effectively, you could use 3 processors to do D, E, and C at the same time. However, because summing up the time taken for B, D, and E is less time than this critical path CNF, you can essentially do it with just the one processor. Do the left branch with one processor and the right branch with the second processor. Because if you had 3 processors here, what would happen is you'd split off to do B on processor 1, C on processor 2, and then you'd split off to do D on processor 3 and E on processor 1. But these would finish and just be waiting around doing nothing. But C would still be calculating along the same time. So you can kind of see sort of splitting up a task into parallel and making it parallelizable is all about sort of scheduling. So the sort of same things that you would learn and sort of intuitively know about scheduling would apply to parallel computing as well. Okay, is everyone happy with this?
What is the correct answer? So 2.
Correct answer is 2, yeah. Well done, Luke. Okay, so that's some sort of intuitive way that you can work out for a specific problem. But there are some sort of theoretical laws that can help you think about this process more generally. So the first one is called Amdahl's law. This is like from the 60s, I think. So this is a very old law. This one actually a law, not an observation. So it's basically looking at a task like we did before, where it's a fixed workload. The workload doesn't change in size. We just want to ask the question of like, what speed up can we get if we apply more resources to this problem? So in this equation, you have big S, capital S is like the speed up, and small s is the speed up that you can get on the parallel portion of your code. And then P represents what fraction of your code, like between 0 and 1, is parallelizable. And then little s is the sort of benefit, the speed up that you can get from parallelizing the parallelizable portion of your code. 1 minus P is just the sort of serial part of your code, kind of like the critical path you can think of as the 1 minus P part. So you don't have to sort of know this graph off by heart, but essentially what it means is the vast majority of problems have some serial part associated with them. And this basically puts a hard limit on how fast your algorithm can be, regardless of how many resources you apply. So this is one thing to remember is like, even if you have a supercomputer, some problems just can't be sped up by using that many resources. So for example, if only 50% of your program is parallelizable, you can only really get a 2 times speed up. And one thing that you notice is you don't get that 2 times speed up when you use 2 processors. You have to go to a much larger number of processors to get that speed up in the end. Okay. So the intuitive part of this is whenever you have some serial part of your code, you're not going to see, if you have 4 processors, you won't see 4 times the performance, unless that serial portion is very small, like going to 0. But there's a sort of criticism of Amdahl's law because it basically assumes that whatever task you're doing is fixed. And you're just saying, given this fixed task, if I apply more resources, what will happen? Okay. Yeah, pretty much. Supercomputers are only really useful if you can parallelize your workload. And to be honest, most supercomputers are actually slower than some of the processors that you would have in your laptops because they're designed for being highly parallel and have a really high throughput. But each individual processor tends to be a bit slower. So for example, at Nottingham, we have Augusta, which is a few years old now, but Augusta's processors run at about 2.5 gigahertz, I think. Whereas most computers that you buy nowadays, like even laptops, will run at about 4 gigahertz. It's not an exact speed up, but your modern sort of CPUs with less cores tend to run faster than CPUs with many cores. And that's usually to do with the thermals and things as well. Does that answer the question? We've got another one coming in. Yeah. So something that someone else added is supercomputer not only gives you access to more processors, but other resources as well. So like memory, a lot of algorithms, for example, if you're doing like quantum states, the number of states grows exponentially and you need a huge amount of RAM to actually represent your states. And yeah, sometimes you might need a terabyte of RAM. You're not going to get that on your laptop. So you have to move to a supercomputer for resources like that as well. Thanks for that. Okay, so yeah, just to recap, there are some criticisms of Amdahl's law, and it's mainly based on this assumption of a fixed workload. So there's this other guy, Gustafson, who basically said that this is not the right way to be looking at parallelizable tasks, because you're only concerned with fixed problem size, but he realized that when people had more resources, they just increased their problem sizes and they were able to actually do more things with it. So we were just talking about quantum states. So if you had more resources, you could just sort of increase the number of like qubits in your state and then work with that instead. And so that's a really important thing to realize is it's not just how much you can get for this fixed problem, but let's say you're okay with waiting like a day for your simulation to finish. If you had double the amount of resources, what problem size could you go to in the same amount of time? So that's the key sort of insight here, is just sort of redefining how you think about sort of speed ups and efficiency. And yeah, so there's a sort of derivation for this. It's basically if you were to take some parallelized algorithm and run it on a parallel computer, it would take like TP units of time. And some fraction of that time is your sort of irreducible time. So the time for executing like the critical path of your code. So your serial execution time is like 1 minus f. And you have f is the fraction of time that's like parallelized. So the idea is basically if you take this result from your parallelized computer and were to run it on a serial computer, how long would it take then? And the sort of maths is quite trivial. It's basically just the time that you spend in the serial stuff plus the time spent in parallel times the number of processors you used or the amount you've parallelized by. And if you sort of work out a lot of the fractions, you get this other scaling law, which is like some constant based on the fraction of time spent in the serial part, plus some like linear speed up by the number of processors you have. And this is kind of what you expect, right? If you have double the amount of processors, you expect to have double the performance, quote unquote. And this S is, you can think of it as a speed up from going from a serial to a parallel, but it's easier to think of it as the slowdown if you take an already parallelized algorithm and run it on a serial computer. So these are just some sort of esoteric laws that talk about parallel computing, but honestly, they miss a lot of key details that are actually really important in implementations. So there are some sort of practical considerations when you're thinking about how to parallelize your workload. So one thing is just sort of scheduling your tasks and like dividing them up between your workers takes time. Like you need to spend resources on being able to divide your tasks effectively. I sort of bundle all of these costs into the term overhead. So there's some overhead for doing this sort of synchronization between your workers, which basically means that even if theoretically your algorithm could benefit from parallelization, it's often not worth it if the problem size is too small. So an example is like if you're working out like a maths equation. So for example, if you want to work out like x plus sine of x, instead of working out or like loading, let's say x squared, just to make this easier. Instead of like loading x, squaring it, and then calculating the sine of x, and then adding them together, you could technically work out the sine of x and x squared independently of each other and then add them. But in scheduling those tasks and making them run across two different computers, you're actually introducing a lot of overhead that takes far longer than any of these operations on their own. So just because something can be parallelized doesn't mean it should be. because you need to make sure that the operations that you're splitting up are big enough that it actually makes a difference. And so, yeah, this sort of synchronization is sometimes also called the communication cost. So if you have a supercomputing cluster, you have individual computers that have to communicate with each other like over the network. And this is often like really, really slow. So essentially you need to make sure your problems minimize these costs, and the sort of benefits you gain from using these multiple processors actually give you a speed up in the end. So it's really important that anytime you do this, you have to test whether the sort of parallelization you've done gives you any improvement at all. Sometimes it might be slower as well. That's something to look out for. Okay, so back to the sort of dependency graphs. Some of the most common forms you'll see or one of the most common forms you'll see, and the easiest, like if you see this, you want to think parallel processing, is what we call a map. So maps exist in normal sort of functional programming. They're used a lot there, but you can kind of think of it as you have like an array of elements and you want to apply some operation element-wise. So for example, y is equal to f of x, where that operation happens element-wise. So this is kind of reminiscent of the broadcasting that we spoke about last week. Yeah, so this is often called an embarrassingly parallel problem because it's so trivial to split up. So one of the ways in which we can do this is by sort of like chunking up the operations, right? So if you have n elements you need to process and like two processors, you can have the first processor do the first n and the second processor do the first n over 2 items, and then the second processor does the next n over 2 items. And that's minimizing the amount of scheduling as well, because you've just given it one big block of data. And one important thing about this process is the execution order is completely arbitrary, right? You don't have to calculate the first element first, and then the second, then the third. You can do the last one, then you can do the first, then the middle. It doesn't matter what the order is. And if you can sort of shuffle these problems around, it means they're good candidates for parallel processing, because you don't know which one will actually execute first when you're doing things in parallel. So as long as it doesn't affect your result, you're fine with that. Okay, so your other operation that's really common is called a reduction. And so instead of having one element go to one element, or perhaps like one element going to 10 elements if it's if you're like expanding something out, which is also a map in some ways, you have this other operation like a reduce. So you can kind of think of this as like a sum. So imagine you're summing up all of the elements in there. You have some dependencies now between all of the operations, and depending on how you're combining elements together, depends on the order you need to do them in. So for example, if you're multiplying 10 matrices together, you can't arbitrarily like swap which order you're doing things in, because you need the commutativity to be correct. You need to like multiply them in the correct order, left to right. But if you have 4 matrices, you can multiply the 2 in the middle first, and then multiply the outer ones if you want to. You just have to make sure you're putting the arguments on the correct side. So yeah, basically the way we can sort of parallelize this, instead of having like a for loop that sums over everything, you can break up the operations into smaller chunks. So yeah, okay, that's visible. So for example, this is a sort of dependency graph, or like a sort of flowchart of how you would add together the first 8 natural numbers. And you can see you sort of have this critical path on the diagonal, and the result inside is just the sort of intermediate sum along the way. So this is sort of typically how you would write a reduction in like a for loop. And so you're just adding into this one variable each time. And the reason why this can't be parallelized a lot is because you have this like one place in memory that you're adding to. So you need to make sure that you're only adding that, or only doing the operations in like sequentially in series. And yeah, basically the next addition that you do depends on finishing the previous one. But the main thing to notice is like addition, like most binary operators is associative. And so you can swap the order in which you do these additions and get the same result. Just again, for reminders, the associativity is basically if you have some operator F that acts on two inputs, like A and B, and then you apply it again to another operator, another argument C, it's the same as if you did A and then F of B and C. With these functions, it's a bit harder to read, but it essentially means that A plus, and then in brackets, B plus C is the same as doing A plus B first and then adding C afterwards. Okay, so the way we can do this in parallel is by sort of taking advantage of this associativity to do the additions in different orders. So we'll do this in steps. So on the first step, what we'll do is we'll just add adjacent elements together. So x1 plus x2 gets stored in some intermediate result here. And you can see all of these don't depend on each other, so you can do them in parallel. All of these four sums can be done in parallel. And then on the next level, you can basically apply the same thing. And you take those two intermediate results and add them together onto the next level, and then add things together there. So instead of having this for loop over n, which takes n steps to calculate your reduction, you're instead halving the number of additions you need to do each time. So if you had infinite resources and you could do all of these 4 additions at the same time, you can basically take this from an O of n algorithm to an O of log n algorithm instead, given you have enough resources. If if you only have like 2 processors, for example, you can speed this up by only a factor of 2 maximum. Because you'd eventually have to like double up the workload between them just to do those 4 additions. That makes sense to everyone. Okay. Any questions at this point?
The x, all should be x3 plus x4, x5 plus x4.
Yeah. Yeah, good spot. Yeah, so what I was saying was the x3 plus x4, I didn't change the indices for those. So those indices should be changed. Yeah, good spot. Okay. Yeah, so just as a summary, between these sort of operations that are really common, you'll find these sort of everywhere in your code. The majority of your sort of parallel operations can be categorized into maps and reducers, and combinations of maps and reducers. So again, map is your sort of bread and butter. That's the easiest thing to parallelize. It's very simple to just chunk things up into sections. And the operations should be able to be done in any order as well. The only problem is you might require some load balancing. So for example, if you have like 3 tasks, like 1, 2, and 3, and you know that the size of the task depends on like the input. So this is like, this will take 1 unit of time, this will take like 4 units of time, and this will take 9 units of time. Your sort of load balancing means that you're splitting up the tasks so that they're doing approximately the same amount of work. So if you had 2 processors, you want to do these 2 tasks on one, and then this task on the other one. Yeah, good question. Thank you. So the question is, would parallel addition be something that compilers do themselves, or do you need to specifically code for them? You need to specifically code for them. And there are good reasons for it as well. So in the case of summation, like let's say you're adding up floating point numbers together, the order in which you add it up is no longer associative because of floating point rounding errors and things that we went over before. And so the algorithm that you choose to do depends entirely on how you're sort of splitting up these addition operations, and the accuracy of which depends on how you split it up. And also, we'll get onto this a bit more on Thursday, but if everything is just parallelized by default for you, that means that if you're nesting your parallelism, you're sort of oversaturating the amount of work each core has to do. And so they're constantly switching between the tasks. And if you do this oversaturation, then it's like you failed your load balancing because you haven't, you're spending more time switching between your tasks than you actually are processing your tasks. So usually it's a good thing to choose when to do it and when not to do it. Thankfully, it's, at least in Julia, it's pretty easy to switch between doing parallelism and non-parallelism. And also there are libraries that already do the parallelism for you. So I was talking about map and reduce. Those are like built-in functions in Julia. You can just access them wherever, but there's another package called threadsx, which I'll just write here. So it's threadsx. And this provides all of those same functions like sum, reduce, map. There's one called fold as well, which is like a reduction, but making sure that the commutativity is correctly accounted for, depending on your operations. But it provides parallel implementations of these algorithms. Okay, does that answer your question? Okay, great. So, yeah, as with both of these methods, doing any scheduling of this work requires a lot of overhead. And so if your operations are really small, sometimes it's just worth keeping them in parallel. Also something on the map, we'll go into more next week, but when we spoke about optimization and like cache locality, that can also come into play here. So if you're doing all of your operations on your array in parallel, you've lost that cache making sure your algorithm is cache friendly. Because if you're doing them all out of order, you can't predict which piece of memory you will need next. And sometimes the serial implementation can be so much faster just because of this sort of cache friendliness. Okay, yeah, and to summarize, reduction depends on the operators you're using. Depends on how to combine things together. So you need to be somewhat careful about that. Also, something we didn't mention is we had the summation that happened in steps. It went from one step to the new step. Oftentimes you need to actually keep track of the memory of these intermediate steps. So in that last example, you'd need an array that's at least half the length of the original array just to store these intermediate results. So these reductions can use more memory as well. And that's very common in most parallel stuff as well, is often you need to keep track of these results independently, so you'll just be using much more memory. And yeah, scheduling introduces overhead. Okay, so just as a sort of small example, this is the sort of prototypical parallel computing hello world example. So you may have seen this before. You can calculate pi by using random numbers. So if you have like a square dartboard and you put a circle that touches the perimeter of your square and you uniformly select random points on that square, you can essentially use the ratio of the number of points that go inside the circle and the number of points that fall in the square outside the circle to calculate pi. And so if you have a unit radius of your circle, then you get this relation. So if you just count the number inside, divide it by the total number of darts, and multiply it by 4, you should get pi, or approximately pi. This isn't a good method of calculating pi, but use something else if you actually do want to do it. But it works as a really nice example. So this is an example of just some code that will calculate it. So all we're doing is we're picking a random x coordinate and a random y coordinate between -1 and 1. Uniformly as well, the rand function gives a uniform number between 0 and 1, and we just times by 2 minus 1 to remap that to the -1 to 1 range. You can calculate the sort of radius from the center of the circle and then compare that radius to 1. In case people didn't realize from the optimization part, you don't need to calculate square roots in this because when you're comparing whether something is less than something else. you can get rid of that calculation. So you can just compare r squared less than the radius squared, which in this case is just 1. So we have two parts to this. We have one part that sort of throws a dart at your board, and the second part which keeps track of the count. So just as a question, thinking in terms of these maps and reducers, what sort of category would you put this in? Any guesses? Yeah, so it's definitely part of a map, that's for sure. Any other insights? It's both, exactly. So this is like a fused operation. It's like a map and a reduce at the same time. The map is a bit strange because you're not actually mapping any sort of input, but technically you are. You're just, this underscore here means you're discarding I. It just so happens that your function doesn't depend on the index at all. So you're doing a map and then you're reducing. So this makes the algorithm a little bit more complicated than just doing a direct map.
Does the underscore mean it's not saved to memory then? Or is it just like a notation thing?
It's just like a notation thing. So it basically just doesn't introduce a variable for that I. So it doesn't pollute your namespace. This is just a completely aesthetic change.
Okay.
You will have to keep track of I somewhere in the memory just to know how many or which part of the loop you're on. Okay, so this is one sort of basic algorithm for calculating it. And you can kind of see that, forgive the diagram, but the bits that you can do in parallel are sampling this r squared. And so each sample you need to do independently of each other. And then your reduction is summing whether r squared is less than 1 together, and then doing some calculation in the end. So one way you can sort of split this up is by, if you have two processors, let's just keep it simple at 2, you can have the first processor calculate half the number of darts you want to throw, and the second one calculate the second number, and then you can combine those results together afterwards. And that's like manually splitting it up. We don't have too much time, but hopefully I can show one very quick example of how to do this. So, we want our function to calculate pi based on some number. We want to keep track of the number inside the circle. And remember, instead of just having 0, we usually use these functions just to make sure it'll work with any type that we put in. That's Python. So what we want to do is basically throw a dart and see where it will land inside the box. So what we can do is just throw an x and y and calculate our radius with just x squared plus y squared. And then we add to our sum whether r2 is less than or equal to 1. And then we'll just return nc over n. Here I've got rid of the if loop by just converting this to a Boolean value, right? So if it's less than 1, this will return the integer 1, and if it's is outside the radius, then it will return 0. So it's the same as, it's just removing the if statement. Okay. So if we add this function in, if we use this, we should get some result.
4 times.
Sorry, yeah, there's a 4 times. Thank you. So run that again. Yeah, okay, so it's approximately pi. So one way you can parallelize in Julia is by using a macro, like most things apparently here. So there's an inbuilt library, space.threads, that basically gives you macros for rewriting your for loops to basically schedule them to run in parallel. So what this threads does on the front is basically say, run each of this inner loop in parallel, and do it sort of automatically for you. If you can also check whether you have multiple threads enabled by querying this. You will need it for your coursework as well, but if you start Julia from the command line, you can have this -t input to basically specify the number of threads you want. There's details in the coursework that tell you how to set this number, but use the number of cores you have on your computer. Don't just set this to a huge number and hope for a huge speed up. Yeah, question. Could you read it out?
Yeah, will that throw an error if it's unparallelizable?
No, it won't throw an error. Yeah, so the question was, will it throw an error if it's unparallelizable? So if it has these dependencies, no, it won't check it for you. It will just assume you know what you're doing. And if you make a mistake, you'll just get the wrong result, which, thank you for asking that, because we're going to show you exactly what that means. So I'm going to just rename this threaded, just so we have a different function. So this is a sort of naive way of doing the parallelism, but does anyone guess what will happen if we introduce this? Happen to our result specifically, not runtime or anything like that.
It'll be wrong.
It will be wrong. Yeah.
Are you storing the NC, the number of zeros and ones?
Yep. This variable here. So I'll just run it and see. You can see that's 2.93. It doesn't seem that wrong, but it's definitely wrong. And usually with Monte Carlo simulations, the more simulations you do, the more accurate it gets. But even if we add another one to this, it's gone to 0.3. That's definitely wrong. So there's something really wrong with how we parallelize it here. And the main issue is this line here, this line number 7. So we have one place in memory that's keeping track of the count inside. And this sort of one line of code is actually multiple operations that happen at the same time. So if we sort of break it down, it's so you have one sort of result of whether it's inside or not, which happens on one clock cycle. But also we've used this plus equals, so this is actually equal to this expression here. And so sort of in the processor, what will happen is it will calculate whether R2 is less than 1, and it will store that in some register. And then it will go and ask memory, what is the value of NC currently? And so the CPU fetches that from memory, which takes some amount of time, and then loads it into the register in the RAM. So that's just one value of memory that you have. It will add that to this inside variable, so the 0 or 1, and then it will store that result back in memory. So in reality, this operation is not just one thing, it's like multiple steps. But you're having multiple processors do that exact operation at the same time. So it's loading something from memory, putting a copy in the CPU, adding it up, and then storing that copy back in memory. So what happens is your cores are racing to put their value in. So if core 1 manages to put their value of the count in, and then core 2 finishes, and then it will overwrite what value core 1 did. And so here you're always going to undercount the number because each core is overwriting the results. And also each summation is different because NC will have changed in memory by the time it's loaded into the CPU of one of them, because another core will have changed it. And so this is one huge thing in multi-threading, which is like shared memory computing or shared memory parallelism. If you're reading and writing, if you're reading from memory in parallel, it's fine, as long as the memory doesn't change. But as soon as you're changing that memory, like in this case, you're writing it, you have to sort of synchronize those operations somehow. You have to make sure that each thread doesn't overwrite each other's result. So this is a bug known as a race condition. This will probably happen in your code at some point. It's very common.
It's a complicated nested for loop. How can you, I mean, you can never know if this result is correct or not. And sometimes.
We could make sure that you're storing each one separately and then.
Yeah, exactly. So there are ways of combating it, but the main thing is here, this is one piece of memory. And if multiple things are trying to read and write to one piece of memory at the same time, that'll be a race condition, regardless of the complexity of your loop. So most of the time you can look at a function and just see that there's a bug straight away. But you have to know that it's a bug to be able to see it. Yep.
Question in the chat from Henry. So as you add more threads, it will actually get less accurate.
Yeah, exactly. The more and more you have this conflicting behavior, the less accurate it will be over time. So there is ways of fixing this for sure. I mean, the main way of fixing it, or like one way of fixing race conditions in general, is to make sure that any operation you do on memory is atomic. And atomic means it can't be subdivided into any smaller steps. So we'll go over more ways of solving this next time. But yeah, this base.threads library introduces the atomic type. So if we go into the REPL, it gives you an example of how to use it. An atomic variable is basically, it guards the memory that it holds to make sure that only one thread can access it at the same time. And it makes everyone else wait until one CPU is finished before another one can use that value and continue. So one way you can use it is wrap this piece of memory in an atomic. And so this is basically the same thing. It's just adding a guard in front of it saying only one thing can access this memory at the same time. And then it also provides a function called atomic add, which takes your atomic value, NC, and basically performs this plus equals for you. But it does it in an atomic fashion, which means can't be subdivided, makes everyone wait. So if we replace this here, and there is one small thing as well. You can't just access an atomic in the same way. You have to use these array modifiers because it points at a location in memory. It's not just like a variable in and of itself. That is all just syntax, so it's not too important. So if we run this again, we get an error. Oh, okay. It doesn't like me. Yeah, okay. It just wanted it as an integer, not a Boolean value. So now you can see that we're getting more accurate results. It will average to the actual true value of pi. The only problem here is this is really slow, right? Using atomics, you're forcing things to happen sequentially. So while you are doing the sort of throwing the dart in parallel, when you're adding it all together, you're blocking things from doing it at the same time. So yeah. We don't have time to like properly fix this, but we'll fix this at the end of next session to make it actually performant. But it's correct. That's your starting point. Okay, so I will close this. Any more questions?
It's a question in the chat.
Okay.
You've basically answered it.
Okay, great. Cool. So we'll talk about this next time. So next time, bring your laptop. Hopefully I can get the theory part out of the way so we can just focus on just doing some problems instead. I'll release the worksheet tomorrow. It'll all be on the website. Yeah, in 2034.